Imagine a force so invisible that you walk through it every single second of every day without even thinking about it.
Right. You breathe it, you move through it, and you probably ignore it unless, it messes up your hair or maybe cancels your flight.
Exactly. And yet, this invisible force is so powerful that it dictates what ends up on your dinner plate. It decides how you build the roof over your head, and it can literally determine the rise and fall of entire economies.
It sounds almost like science fiction, doesn't it? But we are just talking about the atmosphere. And for our purposes today, it's not just weather, it's the incredibly complex churning engine of India's geography.
And today, we're going to pop the hood on that very engine. Welcome, everyone, to this special UPSC-focused deep dive, curated specifically by the Simplified UPSC by PPP YouTube channel.
It's great to be here. We have a huge task ahead of us today. We aren't just skimming the surface. We're really going to drill down into the mechanics of why India's climate is the way it is.
We absolutely are. But before we get lost in the clouds, and I mean that literally,
Yeah.
I have a very humble and immediate request for you, our listener. If you want to boost your retention and really support this mission of making these complex topics accessible, please just take a second and subscribe to the Simplified UPSC by PPP channel right now.
It genuinely helps the algorithm find other serious learners just like you. And, creating these deep dives, it takes a lot of time, a lot of resources. So if you're capable and you find value in what we do, your support on Patreon is absolutely crucial to keeping this whole thing running.
A huge, huge shout out to all of our current supporters who are already helping us create this content. You make this possible. Also, don't forget to like this video and drop a comment. Tell us what clicks for you today or what you want to see next.
And for everyone asking about the materials, because we are going to be referencing a lot of specific text and, importantly, a lot of questions, we've got you covered. There are free notes with practice previous year questions or PYQs available on our public Telegram channel.
Exactly. But if you want the full red carpet experience,
The premium package.
the premium package, getting all the videos in this series at once, plus the premium notes, which have these incredibly detailed explanations, extra PYQs, and model mains answers all organized perfectly, you need to join our private Telegram library.
And how do they do that?
Simple. Just send a DM to us on the public Telegram channel, and we'll get you access.
Okay, I think the housekeeping is done. So what's the mission for today?
Today's objective is a comprehensive audio breakdown of the NCERT Class 11 geography textbooks. We're zeroing in on the mechanisms of climate. That's Chapter 4, the India Physical Environment book, but we're also pulling in the fundamentals of physical geography to explain the why behind it all.
And this is the crucial part of the simplified UPSC approach, isn't it? We aren't just reading the book. We are linking every single concept we discuss directly to previous year questions from 2013 all the way through 2025.
We're going to prove why this stuff matters for the exam. We're connecting the dots, from the fundamental principles like insulation and pressure to how they actually manifest in India's rainy, hot, cold, and incredibly diverse environment.
So are we ready to start at the very beginning with the source of all energy?
Let's unpack this engine, starting with the fuel, the sun.
The ultimate source, right. But here is the first nuance that usually trips people up. The sun itself is a massive nuclear reactor, and it's putting out a fairly constant amount of energy.
Okay, so the output is steady.
The output is steady, but the Earth is a moving, spinning, tilted target. So the energy we receive, which we call insolation, for incoming solar radiation, is anything but uniform.
And if it were uniform, we wouldn't even have weather, would we? We'd just have this stagnant, evenly heated ball.
Exactly. The gradients, the differences, are what create all the motion. Now, the NCERT lists very specific factors for why it isn't uniform. The rotation of the Earth on its axis is one, of course.
But the big one is the angle, right? The angle of the sun's rays.
That's the latitude effect, and it's the most important one. Let's break down the physics of it. Why is a slanted ray weaker than a direct one?
I always just kind of accepted it, but I'm not sure I could explain it.
Think of it like a flashlight. If you shine a flashlight directly down on a table, you get a small, very bright, intense circle of light. All the energy is concentrated.
Okay, that's like the equator at high noon.
Precisely. Now, what happens if you tilt that flashlight?
The beam spreads out into a long oval. It gets dimmer.
The same amount of light is now spread over a much larger area, so the intensity, the energy per square inch, just plummets.
Ah, okay. That makes perfect sense.
But there's a second factor the NCERT highlights, which is just as important. The thickness of the atmosphere the ray has to travel through.
Right. A slanting array has a longer journey through the air.
A much longer journey. It's like trying to shoot a bullet through a thicker wall. It's going to lose a lot more momentum.
So it faces more scattering, more absorption from clouds and dust.
Exactly. More diffusion. So by the time that high-latitude slanting ray finally hits the ground in, say, Sweden, it has lost a lot of its punch compared to a ray hitting Sri Lanka.
Okay, so the sun heats the Earth. But here's a paradox that I've always wondered about. On a really hot summer day, the pavement can literally burn your feet.
Oh.
But if I just stand up, the air at my face level is, bearable.
Yeah.
If the sun is up there, why isn't the air hotter the higher I go? Why is the ground the hottest part?
That is the classic heating from below principle, and it's a core concept. The atmosphere, for the most part, is actually transparent to the incoming shortwave radiation from the sun.
So the sun's energy just passes right through the air.
It passes through without warming it up very much, and it hits the ground. The ground absorbs it, the land, the water, they soak up that energy.
So the ground itself becomes the heater, the primary radiator.
Yes. The Earth then radiates that energy back out, but it does so as long-wave radiation. And the atmosphere, with its water vapor and carbon dioxide, is very good at absorbing that long-wave radiation.
So the air gets heated by the ground, not directly by the sun.
Exactly. It happens through two main processes. First, conduction, that's the air in direct contact with the hot ground getting warm. And then convection, that warmed air becomes less dense and starts to rise, carrying the heat upwards in currents.
And that explains why mountain peaks are so cold, even though they're technically closer to the sun.
They're further away from the main heater, which is the vast heat-absorbing surface at sea level.
Okay. But the textbook, Fundamentals Chapter 9, it mentions a third mechanism that it says is critical for India: advection.
Advection, yes. It's important to differentiate this from convection.
So convection is vertical movement, hot air rising.
Correct. Advection is horizontal. It's just wind blowing heat or cold from one place to another. In the middle latitudes, and definitely in India, most of the day-to-day weather changes we feel are actually because of advection.
And the text gives a perfect Indian example for this, doesn't it?
It does, a very famous one, the Loo.
That dry, scorching wind that blows across the northern plains in summer. It feels like a furnace.
And that's not just the sun heating the air where you are standing in, say, Lucknow. That is superheated, incredibly dry air that has been cooked over the deserts of Rajasthan and beyond.
And it's being transported horizontally.
It's being moved by advection, arriving to bake the plains of Uttar Pradesh and Bihar. That's a classic, large-scale example of advection.
Now, speaking of these vertical temperature changes, we have this general rule that temperature drops as you go up. We call it the lapse rate.
The normal lapse rate, yes.
But sometimes nature just decides to break its own rule.
And that's when you get a temperature inversion. This is a concept that the UPSC absolutely loves because it defies the norm and has so many real-world consequences.
So normally it gets colder with height. In an inversion, it actually gets warmer for a while as you go up.
Yes, for a certain layer. You end up with a layer of cold, dense air trapped right near the ground with a blanket of warmer, lighter air sitting on top of it. It's completely upside down.
What's the recipe for this? I mean, how do you manage to flip the atmosphere like that?
You need a very specific set of ingredients, which the NCERT lays out clearly. First, you need a long winter night.
Okay.
Second, you need clear skies. And third, you need calm, still air.
Let's break those down. Why a long winter night and clear skies?
Well, remember, the ground is the heater, but at night, it becomes the cooler. It radiates heat back out to space. If the night is long, it has more time to lose all its heat.
And if the skies are clear, there are no clouds to act like a blanket and trap that heat in.
Exactly. The heat just escapes rapidly, so the ground becomes ice cold, and the air touching that ground gets cold via conduction.
But the air a few hundred meters up hasn't lost its heat yet.
Right. It's still relatively warm, so you have your layers. Cold at the bottom, warm on top. Now, if there was wind, it would just mix them all up and you'd never get an inversion.
But it's still air.
They separate into stable layers, like oil and water.
This isn't just a textbook curiosity. This was a direct mains question back in 2013.
It was. The question was, what do you understand by the phenomenon of temperature inversion in meteorology? How does it affect weather and the habitants of the place?
The habitants part is the key. Why should a regular person, a farmer in Punjab or a driver in Delhi, care about an atmospheric inversion?
Because that inversion layer acts like a physical lid on the atmosphere, and stability is the enemy here. All the smoke from stubble burning, dust from construction, pollutants from cars, they all get trapped in that cold lower layer.
They can't rise and disperse.
They physically cannot. The warmer, lighter air above acts as a cap, blocking them. This is what creates the infamous Delhi winter smog.
So you get dense fog, dense smog, visibility drops to near zero.
Flights get canceled, driving becomes incredibly dangerous. And for the habitats who are farmers, this is even more critical. Inversion often leads to frost.
Because that trapped surface air keeps getting colder and colder.
And if it drops below freezing, which it often does, any moisture in it freezes directly onto surfaces. This can destroy entire crops of potatoes, peas, or mustard overnight. It's a huge agricultural hazard.
The source text also mentions something called air drainage in this context. Is that the mountain version of an inversion?
That's precisely what it is. Imagine you're in a Himalayan valley. At night, the high slopes of the mountains, with their thin air, cool down incredibly fast.
Okay, so the air on the slopes gets cold.
And cold air is dense, it's heavy. So under the pull of gravity, it begins to flow down the slope just like water.
It literally drains into the bottom of the valley.
It pools in the valley bottom, and in the process, it physically pushes the warmer, lighter air that was in the valley upwards. This creates a powerful inversion. The valley floor becomes the coldest place, a frost trap, while the middle slopes are actually warmer.
Which is why you often see apple orchards and villages built on the slopes, not at the absolute bottom of the valley.
It's a brilliant, real-world example of how a deep understanding of microclimatology dictates human settlement patterns and agriculture. The farmers knew about inversions long before we gave it a fancy name.
That's fascinating. Okay, so we've established heat and its variations. Now we need motion. We need the wind.
And wind is essentially just nature trying to balance its checkbook.
That's a great metaphor. Unpack that for me.
Well, heat creates differences in atmospheric pressure. When you heat air, the molecules fly apart, it expands, it becomes less dense, and it starts to rise. That creates a deficit of air at the surface. We call that low pressure.
And the opposite for cold air.
Right. When air cools, it contracts, it gets heavier, denser, and it sinks. That creates a surplus of air high pressure.
And nature abhors a vacuum, or in this case, an imbalance.
Exactly. Air will always try to rush from the area of surplus, the high, to the area of deficit, the low, to fill that gap. That rush of air is wind. The bigger the pressure difference, the faster the wind blows.
Okay, that makes sense. But here is the thing that confuses everyone, myself included sometimes. If I have a high-pressure area in the north and a low-pressure area in the south, why doesn't the wind just blow in a perfectly straight line from north to south?
An excellent question. And the answer is because the checkbook is on a spinning table. The Earth is rotating.
And this brings us to the Coriolis force.
The famous or infamous Coriolis force, and this was directly in the 2024 prelims.
A statement-based question, right?
It was. They love testing the specific properties of this force. The Coriolis force is an apparent force caused by the Earth's rotation.
So what are the rules of engagement here? What does Coriolis do?
Rule number one, and the most important, it deflects moving objects, including wind, to the right in the northern hemisphere and to the left in the southern hemisphere.
Okay, right in the north, left in the south.
Rule number two, it is directly proportional to wind speed. The faster the wind blows, the stronger the deflection. And rule number three, and this is the big exam trap, it is at its maximum strength at the poles and is completely absent at the equator.
Absent. Zero. Why is it zero at the equator?
It's a bit complex, but it has to do with the geometry. At the poles, the Earth's surface is rotating perpendicular to the axis of rotation, giving maximum twist. At the equator, the surface is moving parallel to the axis. There's no relative twist.
And this absence of the Coriolis force of the equator explains a massive weather phenomenon, or rather, the absence of one.
It explains why tropical cyclones cannot form right on the equator. For a cyclone to form, you need that initial spin, that spiral. You need the Coriolis force to get the system rotating.
So since the force is zero at the equator,
there's no trigger for rotation. Cyclones need to form at least 5 degrees north or south of the equator to get enough of that Coriolis spin to get organized and intensify.
So if you ever see a Hollywood movie with a hurricane hitting a city that's exactly on the equator, you know it's physically impossible.
Bad science fiction, yes, you can call them out on it.
So let's bring this back to India. We've got the Coriolis force deflecting winds to the right. We have a massive landmass and a massive ocean right next to each other.
You're perfectly describing the setup for the Indian monsoon.
The monsoon. The 2014 prelims had a very simple question. The seasonal reversal of winds is the typical characteristic of. And the answer, of course, is a monsoon climate. But seasonal reversal sounds so technical.
It's actually very simple if you just follow the pressure. Let's think about summer. The sun is directly over the Tropic of Cancer. It's beating down on central India. The land bakes. It gets incredibly hot.
Hot land means rising air, which means
A massive, intense, low-pressure zone. Meanwhile, the Indian Ocean, with its high specific heat, heats up much, much slower. It stays relatively cool. Cool water means stinking air, which means high pressure.
so the wind blows from the high over the ocean to the low over the land.
Exactly. And because that wind is coming from the ocean, it has spent months traveling over warm water, picking up trillions of tons of moisture. That is the southwest monsoon.
And then winter comes around.
The whole system flips. The land, with no heat capacity, cools down almost instantly. It becomes very cold. The ocean, however, holds its heat. So now the land is the high-pressure zone, and the relatively warmer ocean is the low-pressure zone.
The wind reverses.
It blows from the land out to the sea, and because it's coming from the land, it's dry and cold. No rain. That complete reversal, that is the heartbeat of the Indian climate.
And it's all driven by this differential heating of land and sea, and something called the ITCZ.
The Intertropical Convergence Zone, you can think of it as the thermal equator. It's the zone of most intense heating where the trade winds from both hemispheres converge.
And it follows the sun.
It follows the sun. When the sun moves north over India in the summer, the ITCZ gets dragged north with it, settling over the Ganga Plains. This creates what we call the monsoon trough, a powerful magnet for those moisture-laden winds coming from the ocean.
Okay, let's talk about the cargo these winds are carrying, moisture.
Wow.
The NCERT Fundamentals Chapter 11 talks about different types of rainfall. Why is it important to know the types?
Because knowing the mechanism, knowing the type of rainfall, tells you where and when it is most likely to rain. It's about prediction.
Okay, so first up, convectional rain.
This is your classic pop-up thunderstorm. The ground gets intensely heated during the day, a pocket of air gets superheated, and it rises rapidly like a bubble in boiling water.
It rises, expands, cools.
It cools, hits its dew point, condenses into a massive cumulonimbus cloud, and boom, you get a very heavy downpour, usually with thunder and lightning, typically in the late afternoon. This is very common in equatorial regions and in the interior of continents during the summer.
Second type, orographic rain. Oro means mountain. Right?
Exactly. This is also called relief rain. This is the story of India's west coast and the northeast. The southwest monsoon winds arrive loaded with moisture, and they smash into the wall of the western Ghats.
They can't go through the mountains, so they are forced to go up.
And as air rises, it cools due to expansion. We call this adiabatic cooling. It quickly cools to its dew point and has to dump all its moisture. That side of the mountain is the windward side. Places like Mumbai, Mangalore, they get absolutely soaked.
But then the air crosses over the peak of the Ghats.
And it starts to descend on the other side. Now, as air descends, it gets compressed by the increasing pressure and it warms up. Warmer air can hold more moisture, so not only does it stop raining, it becomes a dry, thirsty wind.
And that is the leeward side, the rain shadow region.
This is exactly why Pune, which is just a short drive from Mumbai, is so much drier. It sits in the rain shadow of the Western Ghats. It's a textbook example.
And the third type is cyclonic rain, which is associated with fronts and cyclones.
Speaking of storms and thunder, there was a really tricky question in the 2013 prelims about what causes thunder.
Oh, I remember that one. What causes thunder? And the options were things like meeting of cumulonimbus clouds or violent wind.
It feels so intuitive that it's just clouds bumping into each other, doesn't it? It does, but that's completely wrong. Clouds are just fog. They don't crash into each other to make a sound. Thunder is a shock wave.
So explain the physics. What's actually happened?
Okay, so you have lightning first. Lightning is a massive discharge of electricity that heats the narrow channel of air it passes through to about 30,000 degrees Celsius in a fraction of a second.
Hotter than the surface of the sun.
Much hotter. The air in that channel expands explosively. It's a supersonic expansion. Then it immediately collapses back in on itself. That creation of a shock wave is what you hear as thunder.
So the correct answer in that PYQ wasn't about clouds clashing. It was about the violent upward movement of air and water particles, which creates the electrical charge separation in the first place, leading to the lightning, leading to the heat, leading to the sound.
Precisely. It's about the thermodynamic energy conversion. It's not bumper cars in the sky.
Let's zoom out to the world map for a second. Rainfall isn't evenly distributed at all.
Not even close. As a general rule, rainfall decreases as you move from the equator towards the poles. But there's a really important nuance the NCERT highlights. regarding the mid-latitudes and the westerlies.
The westerlies. These are the winds that blow from the west in the temperate zones, say between 45 and 65 degrees latitude.
Right, and since they blow from the west over the oceans, they hit the western margins of the continents first. So in the temperate zone, the west coasts tend to be very wet. Think of the UK, British Columbia in Canada, or southern Chile. The interiors are much drier.
Now contrast that with the tropics, where you have the trade winds.
The trade winds blow from the east. So in the tropics, the eastern coasts get slammed with rain, and the western coasts of continents are often home to the world's great deserts, like the Sahara or the Atacama.
That is a fantastic mental model to have. West coasts are wet in the temperate zone, east coasts are wet in tropics.
It's a general rule of thumb that can help you solve a surprising number of map-based questions.
Okay, moving into part 4. Let's talk about the real beasts of the ocean, tropical cyclones.
These are, in essence, giant heat engines. They run on a specific type of fuel called latent heat.
Latent heat. Can you define that for us in simple terms?
When water evaporates from the ocean surface, it needs energy to change from a liquid to a gas. It steals that heat energy from the ocean water. That heat is now hidden, or latent, within the water vapor.
Okay, so the vapor is carrying stored heat.
A tremendous amount of it. Now, when that water vapor rises and condenses back into liquid cloud droplets, it releases all that stored heat back into the atmosphere.
So the storm is literally being fueled by the heat that is released when the clouds themselves are forming.
Exactly. That released heat warms the air column, making it rise even faster, which lowers the surface pressure even more, which sucks in more moisture-laden wind from the surface, which leads to more condensation and more heat release. It's a powerful self-feeding loop.
And that perfectly explains the primary condition for formation. You need warm water.
The NCERT gives the number, a sea surface temperature higher than 27 degrees Celsius. You need that massive fuel tank of warm water to get the engine started.
Let's talk about nomenclature. We call them cyclones in the Indian Ocean. In the Atlantic, they're hurricanes. Over in the Western Pacific, they say typhoons.
And my personal favorite, in Western Australia, they call them willy willies.
I still can't believe that's the official term in the textbook.
It is. It's right there in the book. Now, the 2013 mains asked a question about the naming convention, referencing a specific storm, Cyclone Phelan.
Why do we even name them? Is it just for the media?
It's not for fun. It's for clarity and disaster management. If you have 3 different storms spinning in the Bay of Bengal at the same time, you can't just keep saying the storm. It creates chaos.
So you need Cyclone A, B, and C.
Exactly. The nations in the region, like India, Bangladesh, Myanmar, and so on, all contribute names to a rotating list. This allows for clear, unambiguous communication between weather agencies, governments, and the public.
There's another great mains question in 2014. Tropical cyclones are largely confined to South China Sea, Bay of Bengal, and Gulf of Mexico. Why?
We can decode this just using what we've learned. What do those 3 bodies of water have in common? They're all relatively shallow, semi-enclosed tropical seas.
Why does enclosed matter so much?
If you're out in the middle of the vast, open Pacific Ocean, you have strong ocean currents that are constantly mixing the water, bringing cold water up from the depths. This acts as a brake on intensification.
But in an enclosed bay.
The water just sits there and bakes in the sun. It gets hotter and stays hotter for longer. You get this deep layer of very warm water. The Bay of Bengal is basically a hot water bath, perfect for brewing cyclones.
Which is why, historically, the Bay of Bengal sees far more and far stronger cyclones than the Arabian Sea.
Historically, yes. But that is changing, isn't it?
It is. Due to climate change, the Arabian Sea is warming up much faster than the global average, and we are now seeing more frequent and more intense cyclones there, like Cyclone Toktai a few years ago.
A very clear signal of climate change.
Speaking of ocean temperatures, the 2017 prelims introduced a concept that was new to many people, the Indian Ocean Dipole, or IOD.
The IOD is huge for India. You can think of it as the Indian Ocean's own internal seesaw.
A seesaw of what exactly?
A seesaw of sea surface temperatures. The IOD measures the temperature difference between the Western Indian Ocean on the Arabian seaside near Africa and the Eastern Indian Ocean near Indonesia.
So a positive IOD, what does that mean for us?
A positive IOD means the Western Indian Ocean, our side, is warmer than average, and the eastern side is cooler than average.
And warmer water off our coast means more evaporation, more rising air.
More rain for India. A positive IOD is a massive blessing for the Indian monsoon. In fact, a strong positive IOD can sometimes neutralize the negative effects of an El Niño. El Niño tries to kill the monsoon, a positive IOD tries to save it.
Then in 2020, the prelims got even more granular. They asked about OMT, ocean mean temperature.
This was a tough, very technical question. It asked for the difference between OMT and the more familiar SST, or sea surface temperature.
SST is just the skin of the ocean, right?
Oh.
The top millimeter.
Basically, yes, and SST is very fickle. A single cloudy day or a strong gust of wind can cool that skin down instantly. But OMT is a measure of the heat content of the upper ocean, down to the depth of the 26 degrees Celsius isotherm.
Which is about how deep?
In the Indian Ocean, that's about 129 meters deep. So it's not just checking the surface temperature, it's measuring the total thermal energy stored in that upper layer of the ocean.
So it's like checking the total charge in the battery, not just the voltage at the terminals.
That's a perfect analogy. And the PYQ confirmed that OMT is a much better predictor of monsoon rainfall intensity than SST because it represents the actual stable thermal energy that's available to drive the atmospheric engine over the entire season.
That is deep. Literally 129 meters deep. Okay, let's move from the ocean to the land. We classify climates to help us organize the world and figure out what to grow. Koppen's classification.
Vladimir Koppen. He was actually a botanist, not a meteorologist, and he had this brilliant insight that the best way to measure a region's climate isn't just with thermometers and rain gauges, but by looking at the natural vegetation.
The plants don't lie.
The plants don't lie. If you see a cactus, you know it's a desert, no matter what the annual average temperature says. So he created this code system using letters, A, B, C, D, E, for the major groups.
For India, the insert text highlights AM as a key type.
Right. A stands for a tropical climate, humid, hot all year round. The little M stands for monsoon. This describes a climate with a short dry season but a massive amount of rainfall during the monsoon season. This covers the west coast and much of the northeast.
What about all?
W stands for winter dry. So AW is a tropical climate with a much more pronounced dry season in the winter. This is the climate of most of the peninsular plateau away from the coast.
And this rhythm of the climate dictates the rhythm of our food plate. The 2013 prelims asked a very direct question: to identify the Kharif crops from a list.
Kharif comes from the Arabic for autumn, referring to the harvest time. These are the crops that are sown when the southwest monsoon arrives in June and July. They are the monsoon crops.
The options on that question were cotton, groundnut, rice, and wheat.
Rice is the quintessential Kharif crop. It needs huge amounts of standing water to grow, which you can really only get naturally during the peak monsoon months. Cotton and groundnut also need that high heat and moisture of the summer season to thrive.
But wheat is the odd one out.
Wheat is a temperate crop. It hates high heat and high humidity. If you try to plant wheat in June in North India, the seed will rot or be destroyed by fungal diseases. Wheat needs a cool, dry growing season. It's a Rabi, or winter crop.
So just by knowing the basic mechanism of the climate, you can immediately eliminate the wrong answer.
Absolutely. Geography is the foundation of agriculture.
And it's also the foundation of soil science. A 2014 prelims question linked the problem of soil erosion to a few different agents.
The agents listed were terrace cultivation, deforestation, and tropical climate.
Wait, tropical climate itself is an agent of erosion. How does that work?
It's because of the nature of the rainfall. In a tropical monsoon climate, you don't get gentle, drizzly rain for months. You get incredibly intense, high-volume downpours. The rain comes down like a hammer.
And if you remove the forest cover through deforestation,
that hammer smashes directly onto the bare soil, breaking its structure and washing it away.
And what happens chemically to the soil that's left behind? The text talks about a process called leaching.
This is a crucial concept for understanding Indian soils. In these hot, wet climates, the sheer volume of water percolating through the soil washes all the soluble minerals like silica and lime right out of the topsoil.
It just filters them down deeper into the ground, so what's left on top?
What's left behind are the heavy, insoluble compounds, iron and aluminum oxides. They don't dissolve easily, they accumulate at the surface, and in the presence of air, they basically rust.
That's why the soil turns that distinctive red color and can harden like a brick when it dries.
That is exactly what laterite soil is. It's the residual soil left after everything useful has been leached away by the intense monsoon rains.
So laterite soil is almost like the skeleton of a soil after the flesh has been washed away.
That is a very vivid, but a very accurate description.
Okay, part 6. Let's address the elephant in the room, climate change. The UPSC is rightly obsessed with this topic.
It's the context for everything we've discussed now. The 2025 mains, for example, asked, how are climate change and the sea level rise affecting the very existence of many island nations?
Now, we all know that melting ice from glaciers and ice sheets adds water to the ocean. But there's another, less intuitive factor at play: thermal expansion.
Yes. It's simple physics, really. As you heat water, its molecules move faster and take up more space. The water expands. A very significant portion of the sea level rise we've already seen is just the existing ocean getting bigger because it's warmer.
And for low-lying island nations like the Maldives or Tuvalu,
It's an existential threat. But the first problem isn't always the land disappearing under the waves. The insidious part is saltwater intrusion. As the sea level rises, the ocean pushes into the underground freshwater lenses that these islands rely on for drinking water.
so they run out of fresh water long before their land is actually submerged.
Precisely. Their homes are still there, but they can no longer live there.
Closer to home, let's talk about the Himalayas, the third pole.
The 2014 mains had a question on the shrinking of Himalayan glaciers. These glaciers are the water towers for all of South Asia. Billions of people depend on them.
And if the glaciers shrink too fast,
The river flow becomes incredibly erratic. In the short term, you get devastating flash floods as the ice melts too quickly. In the long term, once the glacier is gone, the rivers could run dry during the lean season. It's a looming crisis.
there was a very specific map-based question in the 2020 prelims about the Siachen Glacier.
A classic location question. They asked, is the Siachen Glacier east of Cyclone, east of Leh, north of Gilgit, or north of the Nubra Valley?
How do we solve a question like that without having to memorize the entire Atlas of India?
You can use logic. You should know that the Nubra River originates from the Siachen Glacier, and rivers always flow downhill from their source. Therefore, the glacier must be at the head of the valley, which means it must be north of the Nubra Valley.
Deduction over rote memorization. It wins again. Finally, let's look at some of the solutions and mitigation efforts. The 2022 prelims asked about something called the Climate Action Tracker.
This was a tricky organization-based question. They want to know if it's a UN body, a World Bank project, or something else.
And the answer is none of the above.
Right. It's an independent scientific analysis produced by a consortium of research organizations. Its job is to be the watchdog, to track whether countries are actually meeting the emission reduction pledges they made under the Paris Agreement.
We can't talk about mitigation without mentioning nature's own climate technology, wetlands.
2022 prelims had a beautiful question on this. Why are wetlands often called the kidneys of the landscape?
My first thought would be that they hold water, like a bladder. They act as sponges.
That's a common misconception, and they do that. But that's not the primary function of a kidney. Kidneys filter and purify.
Ah, okay.
The correct statement in the exam was that the aquatic plants in wetlands absorb heavy metals and excess nutrients from the water. They trap sediments. They act as a natural water purification system, a dialysis machine for the entire landscape.
So let's try to wrap this all up. This has been quite a journey.
It really is a single connected system. We started with the sun's energy insulation hitting the earth unevenly.
Which creates pressure differences that then drive the winds that get twisted and turned by the Coriolis force.
Those winds then travel over the oceans, picking up vast amounts of moisture, becoming the life-giving monsoon, or organizing into destructive cyclones.
That moisture falls as rain, its location governed by mountains and heat, which in turn determines whether we can grow rice or wheat, and it creates our very specific types of soils.
And finally, we, as humans, are now fundamentally altering the chemistry of that entire engine through climate change, affecting everything from the existence of island nations to the stability of the Himalayan glaciers.
Before we go, I have one last provocative thought for you, a final kernel of an idea to chew on. We talk so much about human-induced climate change. We act like we are the only ones with a hand on the planet's thermostat. But nature has its own trapdoor.
You're thinking about volcanism, aren't you?
Exactly. The NCERT mentions it briefly, but the implications are just wild. Look at the eruption of Mount Pinatubo in the Philippines back in 1991.
That was a massive, massive event, and it didn't warm the earth, it actually cooled it down.
Yeah, was that possible?
It injected millions of tons of sulfur dioxide gas high into the stratosphere. Up there, the gas converted into tiny reflective particles called sulfate aerosols. These aerosols acted like a giant planetary mirror.
So they reflected sunlight back into space before it even had a chance to hit the ground and warm the planet.
Precisely. And the result was that the average global temperature actually dropped by about half a degree Celsius for nearly 2 years. It shows just how fragile the Earth's heat balance really is. A single geological event can temporarily override decades of anthropogenic global warming.
Or, in another scenario, another type of eruption could accelerate it. We are just passengers on a very volatile rock.
A humbling thought to end on, for sure. The Earth can just decide to dim the lights on its own.
Indeed it can. Well, on that note, we have reached the end of this deep dive.
If you found this valuable, if you finally understand why the wind turns to the right or why thunder really crashes, please do us a favor and subscribe to Simplified UPSC by PPP on YouTube.
It helps us immensely. And if you want to help keep this engine running, please consider supporting us on Patreon. Every single contribution helps us create more of this high-quality, research-backed content for you.
And don't forget to check the public Telegram channel for today's free notes and that full list of the PYQs we dissected.
And for the truly serious learners who want the full library, the premium notes, detailed explanations, and those model man's answers, just DM us on the public channel to join the private library.
Please don't forget to like this video and leave a comment. Let us know what clicked for you or what topic you think we should dive into next.
Until next time, keep looking up, keep asking questions, and keep learning.
Goodbye, everyone.
Signing off.